Hello, ladies and gentlemen. So, the following video that we are about to talk about is focused on talking about how exactly we can get off the earth and how much it costs to really do that. All right. So, hopefully you've had a chance to watch the first couple videos on Canvas. Um, our whole focus for this first part of our unit, kind of in space, is focusing on Earth, what's right around it, and how exactly we can get off of the Earth. All right. Then we're going to kind of start moving into what happens once you leave the Earth, what's around us in our solar system, and kind of what crazy things you can kind of start to expect to see as you start to spread out through the galaxy and so on and so forth. All right. So the first piece we're going to talk about is the idea. We're going to elaborate a little bit more on exactly what it takes to leave the Earth. Okay. So if you're going through and you're reading this Google Doc, it's on Canvas, so feel free to take as much or as little notes as you want on this. But for our purpose, we're basically going to focus this as it takes something to get us to leave the Earth. All right. If you watch the video on Canvas that talks a little bit about Earth being a prison, basically we know that the force of gravity is exceedingly good at keeping us on the surface. All right. And basically, if you've ever played Oregon Trail, or at least if you've heard of it, all right, before you're allowed to cross the plains and try and make your way to Oregon, you have to spend a bunch of money in order to basically be allowed to start leaving. Okay, and this is going to be the same thing for humanity in space travel as well. Now, for us, unfortunately, we are trying to pay the Earth something, and instead of paying the Earth cash, which doesn't mean much to the Earth, we have to give it energy in order to be allowed to leave. Okay, so the first three things I actually want you to do, because yes, you're going to have to participate a little bit, is I want you to start by just drawing an FBD of you if you were just sitting on the ground or just standing on the ground. Really, it doesn't matter. All right. So I want you to draw an FBD. That's the first thing. Then I want you to tell me if I decide to try and jump off the Earth, what's going to happen as soon as I leap up. Okay. So as soon as I jump up, what's going to happen? And then what type of energy am I giving myself when I make that leap? And what is that going to start turning into or transform into once I jump up? Okay. So either pause. I would pause the video, take as much time you need to answer those questions. Unpause it. We'll talk about it. All right. So if we had a chance to work through those first three problems, so let's look at it. So if you drew an FBD, if someone's just standing on the ground, simple enough. There's two forces acting on them. There's gravity pulling them down, trying to get them to fall to the center of the Earth, and then there's that normal force from the ground that is pushing back up, making sure you don't fall through it. All right. Now, of course, if you try and jump off the Earth, you're going to jump up, which means literally you're going to start moving upwards. But the moment you jump up and leave the ground, you're going to immediately start to slow down until you basically reach some max height, and then you're going to fall down. All right. Now, when you leap, you are giving yourself kinetic energy because you're forcing yourself to move. Okay. But of course, as soon as you give yourself kinetic energy, as you start to rise off the ground, that kinetic energy is going to start to turn into gravitational potential energy until you get to your highest point, and it's all UG, and then you start to fall back down. Okay? Now, for our purpose right now in this particular classwork, we're going to focus only on trying to jump off the Earth, all right? Which you might find out is pretty infeasible, but we're going to see exactly how infeasible it is. So the world record holder for someone who has for their vertical jump, okay, is held by Evan Ungar. Now this is not like the vertical leap you see at the NFL Combine or the NBA Combine. This is literally a vertical jump, and actually there's a hyperlink in this. You can watch this individual setting the record. All right, but basically his highest jump is he can jump 5 feet 3 inches. All right, and that's the max height he can get to. He has a mass of 80 kilograms. So our first question is honestly, how much energy did he have to start with? How much energy did he have to pay to the Earth to reach that height? Okay? So, if you want to, pause the video here, work through that question. If not, you can let the video keep rolling if you just kind of want to watch and see how we go through it. But, to start with, let's just look kind of what it says on the left side. All right? So, I want to know what it took to get to that height. Okay, and as we just answered previously, we know that it took some sort of energy. Now, our goal is basically we want to know how much kinetic energy did he have to start with so that he could reach that amount of gravitational potential energy that he got to when he got to his maximum height. Okay, so if we solve using energy, we'll say the starting energy is kinetic, the final energy is potential. we know that for gravitational potential, it's just dependent on the mass of the person or the object, the gravity field he's in, and the height of the object. All right. So that would be mgHf. The mass is 8 kilograms. 9.8 is the gravity field. And I've turned 5 feet 3 inches into meters just because that's what we're used to using. So 1.62 meters. So when you go through and make that calculation, when he has reached that height, his gravitational potential energy is now 1,270 joules, which means that he had to pay 1,270 joules to the Earth to get to that height. All right, so his starting kinetic energy would be 1,270 joules. All right, now, right away, that's it's not very easy. Joules are kind of hard for us to understand. We can remember our roller coaster project, we talked a lot about energy, and it took a lot of energy to get our roller coaster up almost, all the way up to those various heights that we talked about. This is one person who's trying to jump. Now, let's say that Evan decides, hey, I've gotten this far, what's a little bit farther? So he decides that he wants to actually try and jump to outer space. Okay? Now, for our purposes, outer space is defined as about 100 kilometers above the surface of the Earth. Okay, so remember, the world record is 1.6 meters. Outer space starts at about 100,000 meters. So how much energy is Evan going to need to pay to the Earth this time to get to that height? All right, so same deal. If you want to solve it, pause the video here, work through how much energy he needs to start with. Otherwise, just kind of relax, wait for a sec, and I'll talk about the answer. All right, so the exact same process we went through previously. We know that to get to this new height, he's got to pay some energy, and in this case, he's starting with kinetic energy. It's all turning to gravitational potential, just like before. So this time, we're solving for the gravitational potential energy of Evan if he was 100,000 meters above the surface of the Earth. Unsurprisingly, it's a lot more. So still the same mass, still the same gravity field. Height is definitely different. It's not 1.62 meters anymore. It's 100,000 meters. And when you calculate that, we get that the gravitational potential energy that he would have when all was said and done was 78,400,000 joules, which would mean that he would need to start with 78,400,000 joules of energy, of kinetic energy specifically, in order to reach that height. Now, with that calculation, I worked backwards and I actually used the kinetic energy formula to find the velocity. You're welcome to check it if you want. Basically, I did it for you. If he was going to do that, he would have to leap up. His launch velocity would have to be 1,400 meters per second, which, hey, that doesn't sound like that much until you convert that to miles per hour, and that is 3,131 miles per hour. And just to give you an idea of how fast that is, let's see the speed of sound. So let's see, the speed of sound is 767 miles per hour, and he would have to jump at 3,131 miles per hour. So that's really fast. He'd break the sound barrier, break a lot of other things too, probably. Okay, now, all kind of silliness aside, just kind of thinking about the idea of someone being able to jump fast enough to get into outer space. The idea is we're looking at the fact that this is the amount of energy, this is the fee that someone would have to pay in order to get something into what we consider outer space. All right. Now, the other issue is that if he somehow managed to do this, if he managed to jump all the way up there, he would run into a problem because as soon as he got up to outer space, what we're going to find out is that gravity does not suddenly disappear there. In fact, gravity is still very much present and he would immediately fall back down. All right. And if you want to, you can click on the link right here. This is the link to Felix Baumgartner, who, when he jumped out of this, I think it was a balloon, I'm not 100% sure on that, but basically he jumped from what we consider to be about outer space and landed, he parachuted all the way down to the surface of the Earth. All right, and it just kind of shows you right there that even though he's in outer space, technically, gravity is very much apparent because it's pulling him straight down. All right, so because of this, we find out that we need something that can consistently apply a force to ensure we don't fall back down. And that is what we're going to find out is the idea of the rocket engine. Okay, so that's just kind of a brief overview of the idea of what fee it takes to exit the Earth. All right, and we're going to keep posting videos. Hopefully we'll have a chance to maybe do a little live discussion. We'll see. But with that being said, ladies and gentlemen, that is where we're going to stop, at least for this particular note set. So I hope you have a great rest of the day,